In this lesson, we're going to talk about relative motion. So the word relative means in comparison to. So we're going to borrow from the Mythbusters series, an episode called Vector Vengeance, where they fire a ball out of a cannon, and the cannon is mounted in the back of a pickup truck. So you can see here we're using vectors. This vector pointing to the left can represent the speed of the pickup truck, and this top vector to the right can represent the speed of the ball. But with reference frames or relative motion, we say there is a reference frame. So are we measuring the speed of the ball with respect to the truck, or are we measuring the speed of the ball with respect to the ground? We can do both. So that's a key idea here in relative motion, is that we have to keep track of our reference frames and what we're measuring with respect to.
Matched as close as they're going to get it, the pressure's on Grant for a perfect release. It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops and it just falls.
Look at that.
Fantastic.
I mean, look, it doesn't move at all. It's going straight down.
Dude.
Woo! We did it! We did it! Yeah! Vector edition! Yeah! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
Okay, so we saw how the ball was fired from the back of the pickup truck. So the first thing we want to do is label our reference frames. So this is very similar to the way the problem is set up on page 72 in the textbook. So I'm going to let my reference frame A be the ground. In other words, how will things look to people, or how will things be measured by people that are sitting still on the ground? And then our second reference frame, frame B, will be the truck. So if you were inside the truck and you're moving with the truck, how would you measure things and how would you see things? And then the soccer ball is the particle, which we'll label with the letter P. So you can see here, if we pick some point on the ground, that's our reference point A, and at some time, the ball is going to be located at position P, and the truck will be located at position B. So my position of the ball, or of P, the particle, with respect to A, is represented by this vector here. So the ball is this far away from my reference point on the ground. Meanwhile, the truck is at a different spot, so the ball's position with respect to the truck is x of P with respect to B, the particle with respect to B. And so you can see, using vector addition, xBA plus xPB equals xPA. So I've written that equation here, and when you look in the book, you see that same setup, and it looks like this. So here is my reference frame A. There's my point A. Here's my reference frame B, which is the pickup truck. There's where the truck is located, and the ball is located over here. So I go back to that helps me to support the equation that I came up with. xPA equals xPB plus xBA. Now let me show you something. There's a little trick you can do just to know you've got it set up right. You see here the subscripts on x are PA. So if you make sure the first subscript of the first term is P and the last subscript of the second term is A, and the internal subscripts are the same, then you know this is set up correctly. So if this is P with respect to A, then here's P, the first subscript, here's A, the last subscript, and internally those subscripts are both B, they're the same. So if you follow that little rule, it kind of makes it easy and mindless to think about it, or mindless to set it up, so you can know you got it correct. Okay, now we're going to take the time derivative of all terms, of both sides of the equation. So the derivative of position with respect to time is velocity, and I do that for all three terms. And what I see is the velocity of the ball with respect to the ground is equal to the velocity of the ball with respect to the truck plus the velocity of the truck with respect to the ground. All right, we're working with vectors, so don't forget vectors have direction associated with them. So for one-dimensional analysis, it's easy. We only have two possible directions, so I'm going to label one direction positive and the other direction negative. You can pick which way, it doesn't matter. So here's my equation that I've set up using my little rule. P is the first subscript and B is the last subscript, so that matches over here. And the inner subscripts are the same. But what you'll find is sometimes you would prefer that the subscripts be switched. So this is a very easy thing to do. If I want to switch x, a with respect to b, if I want to change that to b with respect to a, all I have to do is change the sign on that term and I can switch the subscripts. And so I know this second equation now is a valid equation. I can switch the subscripts and change the sign and everything is great. For example, if the truck is moving with respect to the ground at 5 meters per second in the positive direction, that means if you're in the truck looking at the ground appears to be going the same speed but in the other direction. So the speed of the truck with respect to the ground is plus 5 meters per second, but the speed of the ground with respect to the truck is negative 5 meters per second. In other words, inside the truck, it looks like the ground is moving away from you in the negative direction at 5 meters per second, and to things on the ground, it looks like the truck is moving away from it in the positive direction at 5 meters per second. So let's look at the example of the soccer ball being fired off the back of the truck. So I'm going to find out what was the velocity of the ball with respect to the ground. And what we saw was it looks like that was 0. So if we set up our equation, I don't have to think too hard. Remember, I'm just going to say V, P, B plus V, B, A. I know that's correct because this P and A here, here's my first subscript, there's my last subscript, and the inside subscripts match. Okay, so the velocity of the ball with respect to the truck, if we can make that opposite of what the velocity of the truck with respect to the ground, so let's say, here we go, this is the velocity of the truck with respect to the ground. Let's say it's moving at 30 meters per second in the positive direction. Okay, so that's plus 30. And the velocity of the ball with respect to the truck, if that's 30 meters per second in the negative direction, right? If the truck is moving this way and we fire the ball that way, that means the velocity of the ball with respect to the truck is negative 30. And we can see that 30 plus negative 30 adds to 0. And that is the velocity of the ball with respect to the ground. And that's what we saw. The ball fell straight down to the ground. From inside the truck, it looks like it's moving backwards at the same speed as the truck, but to people on the ground, in their frame of reference, the velocity was 0, and it just fell straight down. Looking on page 73 in the textbook, this is what is called inertial reference frames. So take for an example, you're in an elevator. When you get in an elevator and the elevator begins to move, that's acceleration. And when it stops, that's acceleration. But while it's moving at constant velocity, that's when the velocity of the elevator compared to the ground is a constant. So that is what's referred to as an inertial reference frame. So what we find in that situation, when we take our velocity equation and we take the derivative with respect to time once more, we get acceleration, right? The derivative of velocity with respect to time is acceleration. But over here, this velocity of the moving reference frame with respect to the ground, if it's moving at a constant velocity, that means this is a constant. And we know when we take the derivative of a constant, we get 0. So that tells me that the acceleration of the particle measured in reference frame A is going to be the same as the acceleration of the particle as measured in reference frame B. So the accelerations, the measured accelerations are the same as long as the reference frame is moving, reference frame number 2 is moving with constant velocity with respect to reference frame number 1. And that's what that says right here. Observers on different frames of reference that move at constant velocity relative to each other will measure the same acceleration for a moving particle. All right, let's look now at relative motion in 2 dimensions. We're going to use a simple example here of a river, and in the river, the water is moving to the right, and we can measure its speed with respect to the ground that is in the riverbed underneath the water. At the same time, our boat is going to cross the river. So we're going to measure the boat's speedometer measures its velocity with respect to the water that it's in. So you can imagine, here's the boat, and it wants to go straight across the river. It's pointing straight across the river, and it's going to move straight across the river. But at the same time, the water is moving to the right. So as the boat moves this way, the water carries it this way. So you can see the boat travels in this direction. So that is, we're going to use vector addition again, and that is going to be the vector sum of these 2 vectors. So if I'm looking for what's the velocity of the boat with respect to the ground, right? So I can set up my equation without thinking too hard. I know the velocity of the boat with respect to the ground is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. All I did was follow my little formula, BG there, BG here, and the inside subscripts are the same. Okay, so perhaps we know that the velocity of the water with respect to the ground is 3 meters per second. And I'm going to follow my traditional coordinate system that says on the y-axis, that way is positive, and on the x-axis, that way is positive. That's my choice. I'm just going to, so here we go. I'm flowing, the water's flowing in the positive x direction, so that's plus 3 meters per second. And I know that my boat in still water, if the water wasn't moving, I can measure the velocity of my boat with respect to the water. Let's just say that's 5 meters per second. Okay, so I look here at my subscripts, velocity of boat with respect to the water. I have that value. And the velocity of the water with respect to the ground, I have that value. So that means, now here, don't fall into this trap. This is vector addition. And if this was 1 dimension, 5 and 3 would add together to be 8. But don't forget, this is in the x direction. So if I write that with unit vector notation, 3 is in the x direction. So in unit vector notation, that's the I, and 5 is in the j. So with vector addition in 2 dimensions, I add my x component and my y component with Pythagorean theorem, don't forget. So if I drew it, it would be like this. Here's my vector addition diagram. That would be 3, and there is 5. So I'm showing it here, the tail-to-tail method. If you use tail-to-tail method, remember, use the parallelogram rule. Create a parallelogram. In this case, that's a rectangle, and the sum of those 2 vectors is the diagonal of that. So that's the square root of 5 squared plus 3 squared. So that's the square root of 25 plus 9, square root of 34, and you would get your calculator, and that would be the speed of the boat with respect to the ground. And I could also find this angle that the boat is traveling at. Even though the boat is pointed straight across the river, it's moving at an angle with respect to the riverbank. We'll call that theta. And I know. I know all three sides of the triangle, but I'll use this side and this side. So that's my opposite and adjacent. So theta then is equal to the inverse tangent, using the opposite and the adjacent sides, of 5 over 3. And I plug that in my calculator and come up with my answer for the angle that the boat is traveling across the river at with respect to the shore. So it's easy to forget, but to stress that we're working with vectors. As you see in the textbook, I should have, to be complete, put vector symbols over these to remind myself that I am working with vector addition, and I can't just add 5 plus 3 to give me 8. I have to add 5 and 3 with Pythagorean theorem to give me square root of 34. Okay,